Wisconsin medicine to give us one part of the 2 lecture series on partial identification and in particular moment inequality models. So Xiaoxia is currently the Lowell and Layla Robinson Professor at the Economics Department of the University of Wisconsin at Madison. And she has published many important papers in the literature, and she's currently serving as the co-editor of the Review of Economics and Statistics. So without further ado, let me pass the stage to Xiaoxia to give the lecture.
Thank you very much, Jia. Thank you very much for having me. It's always a pleasure. So Jia told me that this was going to be like a 4-lecture kind of thing. Each lecture is like 75 minutes long. So I prepared four parts. The first part is really introduction of where partially identified models come up. And the second part will be inference for unconditional moment inequality models. So these 2 parts will be today. And 2 days from now, we'll talk about some more advanced topics on inference for moment inequality models, including inference for conditional moment inequality and also for subvector inference in moment inequality models. So this first part is really an introduction of where partial identification comes up. So first, to talk about partial identification, I want to talk about what is identification, right? So identification, I think different people might have different understanding, but most of us could agree that it's about trying to learn about the parameter of interest, assuming that we know the population distribution. If knowing the population distribution, the model structure can pin down the parameter value uniquely, then we say the parameter is point identified. So the model is point identified. If the model cannot pin down the parameter value uniquely when you know the population distribution, but if the model can restrict the parameter to a strict subset of the whole parameter space, then we say the model is partially identified, or the parameter is partially identified, right? So the model restrictions provide some information about the parameter of interest, but it doesn't pin it down to a unique value. But then failing partial identification, then we are in the case where the parameter is completely not identified, right? So the inference for partially identified model is mostly in this interim stage where the parameter is really partially, but also somewhat identified, right? Not point, but partially identified. So where does this come from? Identification really depends a lot on the data that we have, and also depend on the parameter we are interested in and the assumptions we're willing to make. Usually descriptive parameters are often point identified if the data is good enough. For example, if you want to learn about the population mean, if we know the distribution of Y, then the population mean is clearly point identified, right? So that's a descriptive quantity that is point identified. But sometimes the data is not as good as we like. So we want to learn about the population mean, but we do not observe Y for everyone in it. And we don't know the selection mechanism. We do not know whether it is randomly selected or not. In that case, we will not be able to identify even the population mean of Y. So I'll give you an example of this very simple case. And sometimes we are not interested in fact, oftentimes we're not interested in descriptive parameters, but instead we're interested in structural parameters or causal parameters. And the identification of those parameters are much more difficult, and you are much more likely to be in a partially identified scenario. So for example, what can we learn about the causal effects of X on Y when we know the joint distribution of X and Y? Well, without any assumption, we cannot identify the causal effects because we do not know whether there are confounders. So in these last two settings, the one setting is where you want to learn about population expectation of Y, but Y is not perfectly observed. And the other setting is when you observe the joint distribution of Y and X and want to identify the causal parameter, the causal effects of X on Y. Without assumption, usually we don't have any identification, but sometimes we could make assumptions to obtain point identification. For example, if we cannot observe Y for everyone in the population, but if we assume the missingness is random, right? So the population for which we observe Y is the same as the population for which we do not observe Y. Then in that case, the missingness of Y for some individuals will not be consequential for identification of EY. And when so in the second setting, when the parameter of interest is the causal effect of X on Y, now in addition to knowing the joint distribution of X and Y, if we assume that X is randomly assigned before Y is generated, then the causal effect can be identified just as the projection coefficient, right? But in many situations, we think these point identification assumptions are too strong. Like missing at random is often hard to justify, and random assignment of causal variables is also very strong. Without these assumptions, if we don't replace these assumptions with other useful assumptions, then even in these very simple examples, we'll not have any identification. So identification fails completely. For example, in the missing outcome example, if we don't make any assumption, we only know the distribution of Y for those whose Y value is not missing, then EY is completely not identified because it's possible that the missing Ys are all huge numbers. In that case, EY is very huge, positive and very huge. And it's also possible, consistent with the data, that the missing Ys are very large negative numbers in which EY is a very large negative number. So anything in between is possible as well in this case without further assumption. Similar thing happens with the causal effect example because there could be a confounder that has arbitrary correlation with the X variable. And that could mean that we have no way to even bound the causal effect. So no assumption identification is usually hopeless, but in many situations, we think it's too silly, or at least it's not useful to be so agnostic. So unfortunately, most of us are willing to make some assumptions, even though not like missing at random, not strong assumptions like missing at random and random assignment of treatment. We are still willing to make some assumptions because we want to do something with the data. Traditionally, econometrics tries to make the weakest assumption possible to ensure point identification and hope that the assumption made is credible in applications. Well, alternatively, the alternative way to solve this problem is to make a credible assumption and put credibility first for the situation, but then settle with partial identification if that credible assumption doesn't give us point identification. Right, so this alternative is approach that the recent partial identification literature takes. So I mentioned Mansky's the law of decreasing credibility because, you know, Mansky observes that there is a trade-off between credibility of assumption and identification, right? So the stronger assumption you make, the more likely you're gonna get a point identified model, but the strong assumptions are less credible. So how do you achieve a balance is everybody's choice, right? So as I say, traditionally, we aim for point identification, right? So the assumption needed might be sometimes not credible. Well, the new partial identification literature takes the other approach, that's you try to ensure credibility of some assumption, but settle with partial identification. Let's consider an example. So this lecture actually will only be consist of examples. So this is the first example with a missing outcome. This is a very simple example where you are just interested in the population expectation of y, of a random variable y. But y is missing for some individuals and not missing for some other individuals. So let d be the dummy variable indicating missing or not missing. So d equals 1 if y is observed, and d equals 0 if y is not observed. Then, so using the law of iterated expectations, you can write the parameter of interest as the weighted average of the conditional mean of y given the two d values. Well, this is the parameter of interest. It is composed of these 4 components. The 4 components on the right-hand side are not all point identified. So the EY given D equal 1. So this is the expectation of Y for people whose Y value is not missing. This is point identified because we do have the population with D equals 1. And probability of observing Y is also point identified. Probability of not observing Y is also point identified. But the conditional expectation of Y for those whose Y value is not observed is not point identified, right, from this kind of data. So that part is completely not identified. As I said, if you don't make any assumption about this could be positive infinity or negative infinity, then this positive infinity will be passed on to the left-hand side and make EY positive infinity, and so can negative infinity make EY negative infinity. So no assumption is not useful. So we want to make some credible assumptions. Sometimes it is credible to impose upper and lower bounds on the missing Y's. These little yu and little yl are theoretical bounds for Y. For example, if Y is the CDF, the indicator. So expected value of Y is the CDF of W at some given point. Then clearly there are theoretical upper bounds for Y. So 0 and 1 are very credible upper and lower bounds. Or in other case, if Y is an hourly dollar wage for wage earners, then usually 0 is a credible lower bound, and maybe a high number is a credible upper bound. You can use these numbers to get partial identification for EY. Then using this lower and upper bound, if you plug in the lower bound for this non-identified piece, then we get a value that is a lower bound for EY. If we plug in the upper bound, we get an upper bound for EY. So EY is partially identified by these two moment inequalities. Questions? No? You guys should stop me anytime. All right, so with these kind of assumptions, we can partially identify EY. Okay. So in practice, sometimes you can make some more assumptions and see if you can tighten the bounds. One type of assumption is an instrument assumption. So sometimes it's credible to think that there is an instrumental variable Z that affects selection, but it does not affect Y. Okay, so D might be something related to the survey process. Therefore, it affects whether Y is missing or not missing, but it's not related to how Y is generated. So that then in that case, this Z would be a valid instrumental variable that one can use to tighten the bounds. If you have such a Z, then EY would be bounded by these conditional upper and lower bounds. Because EY by assumption equals EY given Z equals little z, and EY given Z equals little z is bounded by this construction, just for the reason that EY was bounded by that construction that we talked about before. So this way, you obtain a set of conditional moment inequalities that can bound the parameter of interest. Sometimes in the literature, there is a weaker assumption that's made, weaker than IV. That's the monotone IV. If you look at the literature, you might see this assumption somewhere as well. So the monotone IV, in this context, it means EY given Z is not invariant in Z, but it's monotone in Z. So we know there is an instrumental variable that affects selection, but it also affects Y, but in a way that we can predict its direction. Right? So EY given Z is monotone in Z. Okay, so if Z1 is greater than or equal to Z, little z2, then EY given Z equals little z1 is greater than or equal to EY given Z equals little z2. Using this slightly weaker monotone IV assumption, you could also tighten the unconditional bound. You could tighten the unconditional bound. This way you can bound the conditional mean of Y given Z equals little z by these conditional bounds for Z equals ZU for all the ZUs bigger than Z. And that provides a tighter upper bound, and you can get a tighter lower bound by considering the Z values that are smaller than or equal to Z. So these are tightened bounds for the conditional mean of Y given Z equals little z. But if you want the unconditional expectation, you just average up these bounds. So that's the way, that's some of the ways to come up with models that you can take to data when like point identification assumption is not credible, but you can make some more credible assumptions. So one paper that applied this approach is this early paper by Blondell, Gosling, Ichimura, and McGeer. They have this paper, they study the CDF of logarithm of weight. they construct bounds for the CDF. So the theoretical lower and upper bound for the missing y is 0 and 1. That is very credible. And here the y is missing because W is missing, weight is missing for people who are not in the labor force. And for people who are not in the labor force, W is not observed. And clearly labor force participation is not random. It's related to the person's wage potential and everything else. So missing at random is not credible in this context. So it's desirable to make weaker assumptions. For example, this bound assumption for the missing variables, and that is very credible. In addition to that bound assumption, they also suggested using some other assumptions that may also be credible in this context to tighten the bounds. One of the assumptions they used is the monotone IV. A monotone IV they used is the out of work welfare benefit income. And they believe that this welfare benefit income affects Y monotonically due to some institutional reasons. So they use this monotone IV to construct the bounds for the CDF, and then they invert the bounds for CDF to get bounds for the quantile. And once they get the bounds for the quantile, they can compute, say, the interquartile range, which is a measure of inequality. Okay. So they use these methods to, on the British data, and this is one of the graphs that they produced using these methods. As you can see, so this data is for wage inequality, which is basically the interquartile range of log hourly rate, log hourly wage. That because of the non-labor participation, this inequality is not point identified. Instead, they build this bound given by these solid lines. If they don't put any additional assumption, only use the 0, 1 upper and lower bound for the missing y's. Y is the probability, so 0, 1 are the theoretical lower and upper bound. If they only use that very weak assumption, then they can get bounds like this. It's kind of wide, but if they put some more assumptions, I forgot what this median only is, but I remember this monotone IV assumption. Using their monotone IV variable that is the welfare benefit, they can tighten the bounds to this. And once the bound is tightened, it looks like they can see a trend over the years from 1978 to 1998. The trend indicates that there seems to be an increase in wage inequality. So, so that just shows you some empirically interesting result that you can get using partially identified models. Okay. So that's the first example. The second example is closely related to the first example. So here it's also interval outcome, but it's in a regression context. Here in this example, we are interested in, let's say we're interested in the model for y, say the conditional mean of y given x is this linear function of x, and we are interested in the parameter in this conditional mean model, the theta parameter. Again, instead of y, we do not observe y, but we can only have some bounds, capital YL and capital YU, that we know will bound y. Then we are not able to use this moment condition, moment equality condition, because y is not observed. But if we replace y by YL and YU, we'll obtain a bunch of moment inequality constraints. And these moment inequality constraints could partially identify the model, and we can take these moment inequality constraints to the data to do inference about theta parameter. Questions about this? Right, so these intervals YL and YU, I didn't talk about where they could come from. These are different from the little YL and little YU for the missing variables that we put, because this little YL and little YU are non-random numbers. Well, these capital YL and capital YU are random variables that are known to bound Y, at least in conditional expectation. Often this capital YL and capital YU can be constructed depending on what context, depending on the reason that Y is not observed. So for example, if Y is missing for some people, then, so if Y is missing for D equals 0, just like the first example, then you can construct YL to be Y for those whose Y is not missing, and little YU for those whose Y value is missing. Then the capital YL and capital YU constructed this way will be bounding Y with probability 1, right? So that's one way where these bounding variables may come from. Then using these bounding variables, you can come up with these conditional moment inequalities. Example 2.1 is, so it's basically a variation of the second example. Here, instead of a regression model, we have an IV regression where some of the X variables might be endogenous, but instead it is error term U is mean independent of an IV vector, instrumental variable vector, Z. Again, Y is not perfectly observed, but we have some credible bounds, YL and YU, that bounds Y at least in conditional expectation. Then we can construct these moment inequalities as well using YL and YU. Okay, so I'm talking about where do the intervals typically come from here? And I already talked about this missing outcome. And there is another source for the interval that might be bracket measured outcome. And sometimes in some surveys, individuals are not required to report their exact value of, say, income, but they are asked to choose from several rough brackets, or individuals are given choices. If they don't want to report exact numbers, they can choose to report some brackets. And maybe some individuals will not report anything. Maybe some will report the brackets and some will report Y, their Y, precise value of Y. Then in that case, you can still construct this capital YL and capital YU as the bounding variables for Y. Okay. And a different example, kind of a more structural example for interval outcome is in this paper, this paper of mine with my colleague Amit Gandhi and my student Zhantong Lu. In this example, we study the demand of products that people only buy at most one in a time period. For example, like vehicles, right? So it's the demand model, discrete choice demand model. In those discrete choice demand model, what people usually do is to construct a inverse demand function. And that inverse demand function is a measure of the utility, the random utility that the product gives the consumer. And that random utility depends on the product's characteristics, both observed and unobserved. And then once you get the inverse demand, you have a measure of the random utility. And you can study how the observed characteristics affects the random utility. And because, so once you have the inverse demand, that's the constructed random utility, you basically have an IV model, right? Because some of the product characteristics may be endogenous, like price might be endogenous. So they come up with instrumental variables to relate the inverse demand with the observed characteristics and try to estimate the effect of the observed characteristics on the inverse demand. Okay, and in a very simple example where you have a logit error and only one product, so the consumers are deciding whether to buy that product or not to buy that product. Let PT denote the probability that the product is bought. Okay, in that for PT is the probability that a random consumer in that market buys the product. Then, according to the demand model, the inverse demand would be log of PT. That is the measure of the random utility. Log of PT is modeled by this observable part and this unobservable part. Observable part is given by xt times beta, where xt is observable product characteristics, including price, and ut are the unobservable characteristics. And xt might be correlated with ut, and they might have an instrumental variable. So once you get the inverse demand, this becomes a linear IV model, okay? But the problem in this case is when you try to apply this on some of the data sets, you find that this inverse demand is not perfectly measured because it depends on this choice probability PT. And the choice probability PT is often measured with error because choice probability is often measured using the sample choice probability of a finite sample of consumers. So that is often measured with error. And in the most extreme case, this measure ST constructed from the model can be zero, as I said. So in the extreme case, for many data sets, you can observe ST to be zero, even though your model still implies that the choice probability PT is not zero. It's possible that the difference between ST and PT are not very large, but because you use the data on ST through a logarithm function, the logarithm is going to blow up any small difference between ST and PT when PT is small, when the choice probability is small. That's simply because logarithm has huge slope around zero. So in that case, just using ST to replace PT doesn't work. So what we come up with in that paper is to modify ST by a positive number. So ST could take value 0. It's possible that this product is just not purchased by anyone in the market. Okay, that's simply because in many these demand data sets, the market is defined to be a weak. Like, for example, a product is a certain brand of cereal, and that cereal is not a very popular product, and nobody buys any unit of that cereal in that week, then the choice probability of that cereal in that week will appear to be 0, even though theoretically there could be still some consumers who would buy it. It just so happened that nobody did. So ST could be 0. So we modify it by a positive number, C, divided by NT. NT is the number of consumers who came to the market. If you don't modify this, so because ST can take the value 0, log of ST can take the value minus infinity, the expectation of log ST doesn't exist, is minus infinity, right? But if you do modify it, it becomes a finite number. The expectation becomes a finite number. And in fact, for any P, we know the distribution of NT times ST, which is a binomial distribution with parameter NT and P. For any P, we can find a C so that expected value of log ST plus this modification equals what we want to put there, which is log P. So we can find a C that can make this a unbiased estimator of log P. And that's going to, if we know that C for the appropriate P, then we can construct a moment equality, conditional moment inequality to solve the problem, to take to data and to do inference about the parameter. But of course, the problem is that we do not know the true choice probability. If we did know it, we don't even have to do this. We do not know it. But we can get a function C as a function of P. So we kind of can get an upper bound by taking the supremum over all possible P's, which is between 0 and 1, and get a lower bound by taking the infimum over a large set of P's. Then if we assume that P is belonging to this large set, that interval, then this modified share with the upper bound will give us a half unbiased estimator for log PT. It's half unbiased because it's not going to be less than this. It's greater than or equal to the target we want to estimate. And if we plug in the lower bound, we give the other half unbiased estimator. So we get an upper bound for log PT and a lower bound for log PT by plugging in different values for the modification. So that's the way we come up with, so if you think of this as Y that is not observed, we come up with a YU and a YL, that bound Y in conditional expectation, okay? And of course, you might wonder what this CU and CL, this upper bound and lower bound might be. Is this CU very big? Is this CL very small or something like that? We numerically calculate what this CU and CL is in almost all the scenarios possible. And we find that CU is not very big. It's basically only needs to be as big as 0.5. And CL does depend on the lower bound you allow for PT, but it's approximately that lower bound for PT. So the credible assumption you put in there is a minimum value for PT, or an assumption that you put in there that will result in this bound is a lower bound for PT. Once you put in that lower bound, you can construct this conditional moment inequalities to take to data. And oftentimes this lower bound is quite credible because we don't need this to be a large number. Often this can be very, very small, right? Like 10 to the power 25 or something like that. So that is often a credible lower bound, and that assumption will lead to this conditional moment inequalities that we can take to the data, right? So, right. So that is our YU, and that is our YL, and that is the Y that we do not observe. Right. So once we have those, we can construct these conditional moment inequalities to take to data.
Yeah, I think there's a question in the chat if you want to address that quickly.
I can't see it. Yeah, let me see.
Just the last message. You can take a look.
Okay. Yes, so Andrew Tia asked me whether this is the BLP with zeros. Yes, that is the paper. Do you have follow-up questions about this? Are you muted? Or you're not muted, but I cannot hear you.
So we do have a Q&A part. So after your formal lecture.
Okay.
So during the
Okay,
break,
so I will just go on. Yeah, sure.
Talk more. Yeah.
Okay. So so this conditional moment inequality is typically partially identify theta naught, but it could also point identify theta naught. Or it's also very simple to see when it point identify theta naught, or if these bounds collapse to one, collapse to the same variable for a positive measure of z, then typically this model can point identify theta naught. And we take that approach in Gandhi, Liu, and Xu as well. So that's the second example. And the third example is regarding entry game with multiple equilibria. So when estimating entry games or games with a discrete number of players and a discrete number of actions, the traditional empirical approach is to compute the model predicted probabilities, and then using this model predicted probabilities of game outcomes. Using this model predicted probability of game outcomes, we can set up either moment matching conditions or maximum likelihood to estimate the model parameters. So that's the traditional approach for these discrete games. But then both the moment matching approach and the maximum likelihood approach require a well-defined prediction for the game outcomes, or a unique prediction for the game outcomes, right? But if the game has multiple equilibria, no such prediction exists unless you assume a selection mechanism for the equilibrium when there is multiple, right? So when there are multiple equilibria, that prevents us from getting a unique prediction for the outcome probabilities, we cannot use the traditional moment matching or maximum likelihood methods. And often so many papers assume selection mechanisms. The selection mechanisms in the case of multiple equilibria is very hard to justify because the theory really doesn't tell you which one is the empirically relevant one. But it may be easier to justify in some contexts than others, but in many contexts, it is not very easy to justify. So people think that maybe we don't have to assume this equilibrium selection rule, and we can come up with an incomplete model that leads to partial identification, right? So just to be more specific, we can consider a simple example with two firms and two actions, enter and not enter, right? So this enter, and this is stays out, not enter. a market. So there are two firms who are choosing whether to enter and not to enter. And in this game, let's assume complete information, meaning that every firm knows their own and their opponent's payoffs completely. Okay, they know their payoffs completely. These are the payoffs, and they play a simultaneous move, Nash equilibrium. Let's say these are the equilibrium. When no one enters, they both earn zero profit. When both enters, they earn duopoly profit. And when firm one enter and firm two doesn't earn any profit, but firm one earns monopoly profit, right? And it's analogous here. When firm one does not enter, but firm two enters, firm one earns no profit, but firm two earns monopoly profit, right? So these are the payoffs of the firms. As you can see, there is this delta parameter that are quite interesting for many problems. They indicate the computation effect between the firms, right? When delta one, delta two, these are often assumed to be negative. So these are just the discounts in their payoff caused by the participation of the other firm, right? In these complete information simultaneous move game, there are different ways that the game can play out depending on the shock, the payoff shock of the two firms. So here, this graph is shown a lot in partially identified literature. And this graph just says that when the unobserved shocks is very large, like in this area, then the market is very profitable for both firms. Both firms will enter, even though they know that the other firm also enters. Even with the computation, they are still making positive profit. Then the model predicts 1-1, both firm enters. So that's a unique equilibrium outcome in that scenario. And when the market is not profitable, when epsilon is small, then no firm will enter. They do not want to enter even when they are them, even when they could be the monopoly of the market, right? So in that case, when epsilon 1, epsilon 2 is in this very low region, the model also predicts a unique outcome. So with 1-1 and 0-0, the model do predict a well-defined choice probability or outcome probability function. But there is an area where the market is not too good and not too bad for both firms. They would be happy to be there if they are the monopoly, but they would want to get out if they are one of the duopoly. In that case, the model would predict a multiple equilibria setting, right? So it could be one firm is there, the other firm doesn't want to enter, or the other firm is there, but the first firm doesn't want to enter, right? So both of these are Nash equilibrium. And if there is no equilibrium selection rule, we do not know whether 0-1 happens or 1-0 happens. So because of this multiple equilibria, the model cannot predict a well-defined probability function for the outcomes 1-0 and 4-0-1. So, so this is basically the mathematical forms of what I just said. The model is able to predict the probability of 0-0 happening and the probability that 1-1 happening. It's also able to predict the probability that 0-1 is the unique equilibrium and 1-0 is the unique equilibrium. You can also predict the probability that 0-1, 1-0 are the multiple equilibria, from the multiple equilibria. However, unique 0, 1, unique 1, 0, and multiple, these are not observed outcomes. When you observe 0, 1, you do not know whether it's unique or one of the multiple, right? So these are not observed outcomes. So these probabilities cannot be taken to the data. Instead, what we can do is to, so the traditional approach is to assume a selection mechanism when there is multiple equilibria, and then the model can predict the probability of 0, 1 or 1, 0. But instead of assuming equilibrium selection, we can also just bound the probability of 0, 1 and probability 1, 0. A lower bound is easy, right? 0, 1 can occur when either it's a unique equilibrium or it's one of the multiple. Therefore, the probability that 0, 1 is the unique outcome, unique equilibrium, is a lower bound, and the probability of unique 0 and probability of multiple, the sum of the two, is an upper bound for this. And same thing for probability 1, 0. You can come up with these bounds for the two outcome probabilities that cannot be predicted by the model. So combining all of these model implications, we can come up with a set of moment equalities and inequalities. So these conditions also potentially partially identify theta. So that's another example. So there are many papers that apply this approach on IO data and on network data. So these are some of the examples. So the fourth assumption, the fourth example is reviewed preference inequalities. So this is another way that inequalities may come up. So the most representative paper may be this Pecos, Porter, Ho, and Ishii paper. They argue that in discrete games, traditional approach runs into the problem of multiple equilibria, but that's not the only problem. There is another problem, that is, if the choice space, the action space of the players is very big, it's going to be very difficult to solve for equilibria, okay? Especially if there are multiple equilibria, if you want to enumerate all the possible equilibria, that is often a very difficult problem to solve. But then they observe that maybe we don't have to solve those games. We could just form inequalities using reviewed preference. So reviewed preference is a super simple principle, which simply says the action chosen are better than action not chosen. You wonder, this is quite obvious. It's just implied by the rationality of the agents participating, right? So why did the actions were chosen? Because they were better, right? Because the agent is rational, right? So the reviewed preference is a very intuitive and credible thing to assume. This is a very simple idea. It can be used to construct moment inequalities. But of course, there are complications because reviewed preferences, when you want to specify the, when you want to turn the reviewed preference principle into moment conditions, you need to solve several structural modeling problems. Like one is, what's the information set for the players? So that is important for determining what we mean by better, right? What we mean by one action is better than the other action, right? So in the decision under uncertainty context, the better is typically modeled by conditional utility, but then what are you conditioning on? What are you conditioning on? That is the information set for the players, right? That needs to be specified in order to write down the reviewed preference inequalities. And also, it's also important to relate that to what we know, what the researcher know in the data, because what we know in the data is the thing that we can take to data, right? You can form a reviewed preference inequality conditional on the player's information set, but if we do not know the variables in the information set, the inequality that we set up is not really empirically relevant. We cannot take them to data. Just to fix ideas, we can consider this 2x2 entry game again. Now, suppose we assume it's complete information and simultaneous move, just like before. You can set up the firm's reviewed preference this way, right? So this is the utility. So, so here are the Y's. Y1 is the action of firm 1. Y2 is the action of firm 2. They are binary variables. Take the value 1 and 0. So this is the utility of firm 1. When the firm 1 take the action that the firm actually took. So the capital Y is the action that firm 1 actually took. So that's the utility that for firm 1 when the firm takes the action he actually took. And this is the utility for firm 1 when the firm takes the action that she didn't take, right? So this is the counterfactual utility or counterfactual payoff. That is the actual payoff, and that is the counterfactual payoff. The actual payoff should be bigger than the counterfactual payoff because the capital Y1 is the action taken. But then when you contrast these payoffs, to set up the reviewed preference inequality, you want to specify the information set. When we assume complete information, the information set is all the X and all the epsilons, right? So these two inequalities are the inequalities defined by or implied by the reviewed preference principle. Well, these inequalities are easy to set up, but they cannot be taken to the data. They are not empirically useful because these unobservables appear in the model and also appear in the conditioning set. Right, because these epsilon 1, epsilon 2 are not observable. So we cannot take these to the data. And clearly given X, we probably cannot assume that epsilon 1 times Y1 has mean 0 because Y1 is an endogenous variable. Okay, so this cannot be just taken to the data. One way to get around the issue is to make an alternative assumption about the firm's information set in this case. You can assume instead the firms do not know everything, so it's not a complete information game. Assume that the firms do not know the unobservables when they make the decision. If you assume that the firms do not know the unobservables when they make the decision, then epsilon 1, epsilon 2 does not appear here, right? Does not appear in the conditioning set when you set up the moment condition models. And not only that, but also because the firms do not observe epsilon 1, epsilon 2 when they choose their action, the actions also do not depend on epsilons, right? These actions are also not dependent on epsilons, and therefore it's maybe credible to say that the epsilons are mean independent of the actions and the X variables, right? Because the epsilon is realized after the action is taken, okay? Then once you make this assumption, you can get rid of the epsilons from the model, and you have a set of moment inequalities that only depend on observables, and these are empirically feasible. You can take these two data to estimate the alpha and the deltas. So this example just illustrate, sometimes it's tricky to set up these moment inequalities using reviewed preference principle. The information set of the players is important. Okay. So there has been a very large body of empirical work that has been carried out using this reviewed preference approach. Many of these are Areopac students and some are not, but they have very successfully used these approaches, this approach on many interesting empirical problems, including like hospitals' referral choices, including banks' ATM choices, and exporting, and PC, and so on and so forth. So, all right. So this lecture is just about the examples, and we will focus on the theory of inference for the next few lectures. Any questions?
So we can take some questions and take a break if you want. And then afterwards, you can continue with the second one.
Okay.
So if anyone has any questions, please just raise your hand. Yeah. So I think Andrew has this question. Andrew, please unmute yourself and ask a question.
Yes, thank you for the lecture. So my background is that I'm interested in BLP and its related applications, right? So full disclosure, I'm working on a paper looking at applying machine learning techniques like automatic differentiation for the robust estimation of BLP, including into demand plus supply. I wanted to ask for your bounds estimator, right? How does that, perhaps it's a bit dirty to ask a computation question in a theoretical lecture, but how does that influence the computation of the objective function? And does it open up your method to some of the criticisms, for example, in Nittel and, I'm so sorry, I'm going to butcher this name, Metasoglu? Their criticism that BLP estimators are unreliable. Yeah.
Because it's hard to compute, right?
Yeah, and now you're adding additional new and exciting things, which looks theoretically amazing, but having not done the differentiation of the moment conditions myself, I don't know how you would do it unless you resort to some sort of finite differences estimate.
Differentiation of the...
Because in the estimation, when you run GMM, usually you will run a gradient-based optimizer like LBFGS or something, right?
Yeah, because you're worried about the numerical integration, right? With the numerical integration, some of the moment function becomes non-differentiable. Is that what you're worried about? Yeah.
Yes, and then I don't know if you consider this in your paper. I'm sorry, I sort of skimmed it and I couldn't really look at it. I assume that when you implemented BLP, you only did demand side. You didn't add in the supply side as well.
That's right. We only did the demand side.
Because what I found, I'm sorry if this is taking too long, feel free to cut me off.
No,
what I found is that when you include the supply side, and here I'm working off Conlon and Godmaker's paper in that, I mean, everybody knows that paper from the subfield, right? You have this inversion of the shares matrix as part of the computation for the supply side and the markup. And when shares are small, that generates a lot of numerical instabilities. And I don't know whether further modification of the moment function will only amplify these instabilities. The hope is that it will cure them.
Would help with the instability because you will not be taking the inverse of zeros anymore, right? I think that part of the instability probably would not exist, but the numerical integration is still a problem. So computation-wise, the bound approach is the same as the traditional BLP. If someone could apply the traditional BLP in a model, you could apply the bound approach as well. So if this instability, as you said, in some contexts is caused by this close to zero issue, then our modification would help in that case.
Okay.
Yeah.
And
yeah, I'm not really an expert on computational VLP because I've never done it myself. my co-author who is more of an expert. But I do realize that there is such a problem. We have a different paper with also Zhantong Lu and another student that explores other ways that can help you to avoid doing that inversion. So you don't have to do the inversion of the demand. I think that could probably help with computation.
okay, thank you very much.
So
Thank
Chen
you.
Ying has a question.
Yeah, hi, Xiaxia. Thank you so much for this great lecture. So from my superficial knowledge, what the 2 points that always keep me away from using moment inequality, first is that I'm afraid the bound is too wide to be informative. And the second is how to do counterfactual exercise. And because I'm actually doing international trade, so a lot of our work need to do counterfactual exercise on policy implications. Right. Yeah, right. So just from that 2 points, how should I tackle those, or is there any refinement, or what some procedure I can use? Yeah.
Yes. So for whether the bounds are too wide, in fact, what people find in I mean, it depends on the application, but in the empirical papers that I read in this that use these approaches, they normally can get quite informative bounds. And oftentimes with if you use conditional moment inequality, the information provided by the inequality can be a lot. So the wideness of bound often is not a problem, especially for structural models. If you're really just doing what Blondel, Gosling, and Ichimura and Maguire are doing, it's a reduced form bound for the population mean of Y. In those kind of problems, the bound could be really wide. But for structural models, even when you are doing moment inequality approach, you're still making a lot of structural assumptions. And because of that, often the bounds are not very wide in my experience. And the other question that you had about doing counterfactual. Counterfactual, as I understand, is a function of the parameter, right?
Yeah.
So you estimate the model and then you plug the parameter estimates into the model again and change something to get some result, right? So it's a function of the parameter, to put it simply. So there are ways to just focus on the functional parameter, to inference for the functional parameter. And that can be easier than just calculating the big confidence set for the parameter and then plug every possible value into the model to get the counterfactual. That's broadly speaking is the subvector inference part that I will talk about tomorrow. So that the methods in that literature could be helpful for doing counterfactual using moment inequality models.
I see. Thank you so much.
Thank you.
I think that is all the questions for now. Let's take it. Xiaoxia, how long the break do you want to be? 15 minutes, 10 minutes, your choice.
Oh, okay. So maybe 10 minutes?
10 minutes. So okay. So we take a 10-minute break and then we come back for the second lecture.
Thank you, yeah. Thank you, everyone.
So we're back.
Yep.
Ready to start?
Okay. Okay, so can I start now? All right, so this part will be about inference for a particular type of partial identified models, which is the unconditional moment inequality models. So many of the partially identified models studied in the literature reduced to a collection of inequality moment restrictions, some inequality restrictions on certain moments. Some of these inequalities are about unconditional moments. That is, there are finite number of moment conditions required here. Here in this model, the MJ is a known moment function. W is a vector of observables, and theta naught is the unknown parameter. There are some equalities and some inequalities. And some of the models reduce to moment inequalities that are conditional on some instrumental variables X. So the conditional moment inequalities models, because they imply an infinite number of moment restrictions, they are a little bit more complicated than the unconditional ones, right? So they are more complicated than the unconditional ones if the conditioning random variable can take more than a finite number of values. So let's start with the simpler model. That's the unconditional moment inequality models. And as I wrote on the previous slide, this is the general form of unconditional moment inequality models. Here we have a P number of moment equalities and K minus P number of moment inequalities. And these thetas are unknown parameters. W is observable random variables, and MJ are known moment functions. And this capital theta is the parameter space. And because the model is defined by inequality restrictions, we may or may not have enough number of equalities to point identify the parameter. So the true value of the parameter may or may not be point identified. And often people define the set of values in the parameter space that are consistent with all the moment inequalities or equalities. Okay, so that is the identified set for the moment inequality model. Clearly, if the model is correctly specified, the true value is in that identified set. And we do only limit the discussion to correctly specified models. So the true value is in the identified set, but the identified set may not be a singleton, so it might contain other values as well. So that means even if you have an infinite sample, that is, even if you have perfect knowledge of the population moment function, you still cannot uniquely pin down theta naught. That means you cannot distinguish theta naught from other elements of the identified set. So therefore, it's impossible to consistently estimate theta naught, right? Because even if you have infinite amount of data, you cannot pin down the true value. So consistent estimation of the true value is not possible. So since the points in theta naught are not distinguishable from theta naught by data, it makes sense to treat all the points in the identified set as potential true parameter values. And one reasonable thing that people might want to do is to treat the identified set as the estimation target, as we just try to estimate the identified set. That's an intuitively very natural idea. So it's a very natural idea to want to estimate this identified set. But sets are different from points. So they belong to a different metric space. So a natural metric on the space of the sets is the Hausdorff distance, which measures the maximum distance of points in theta hat to theta naught and measures the maximum distance of points in theta naught to theta hat and take the maximum of these two maximum distances. And that is the Hausdorff distance. If the Hausdorff distance is 0, then these two sets are closed. Their closure are the same, right? And the hope is to find an estimated set that satisfies Hausdorff consistency, meaning that the Hausdorff distance between the estimator and the target set goes to 0 in probability. However, the trouble is that is a difficult task in a lot of problems. So consistently estimating the identified set is much harder than consistently estimating a point identified true parameter value. The simple reason is that the identified set contains more than one value. Right? It's not difficult to get at part of the identified set, some points in the identified set, but it's much more difficult to get at the entire set to find all the points that may satisfy the moment condition. To illustrate the difficulty, let's consider a slight stylized example with just 2 moment inequalities and 2 parameters. So these are the 2 linear moment inequalities with 2 parameters, theta 1 and theta 2. This is not realistic. It's just an example to illustrate that consistent estimation is difficult in this context. Suppose that under the true data generating process, EX1 and EX2 are zeros. Then the identified set is easy to find, right? Because EX1, EX2 are 0. So really the restrictions are just theta 1 is greater than 0. Theta 1 is less than 0, right? So that pins down the value of theta 1, but leaves the value of theta 2 completely unconstrained. So the ID set is the whole vertical axis. Okay. The identified set is the whole vertical axis. But now suppose you don't have infinite amount of data, but you have a finite amount of data. Therefore, you don't have the expectation of X1 and X2, but instead you construct the sample mean estimators for the population expectations. These X1n and X2n may be very close to their expectation counterparts, but still they're not the same, right? Especially they are not the same. The population counterpart is 0, and the samples, maybe they are close to 0, but they are typically not 0, right? With probability 1, they are not 0, right? So now this is the finite sample analog of the moment inequalities. So if you define a set estimator that is kind of a sample analog of the ID set, right? So you just replace the expectation by the sample average. And that is a sample analog for the identified set. So let's say this is the theta n hat, right? So this is the estimator you would use in a just identified traditional GMM model, right? In a method of moment model, this is the parameter estimate that you would define. And here, let's say we use this estimator. What's gonna happen to the Hausdorff distance between the set estimator and the identified set? You're gonna see that the Hausdorff distance is with probability 1 infinity. So it's not going to converge to 0 at even when n goes to infinity. Right. So the reason is very simple. We can, try to figure out what this set is for different configurations of x1 and bar and x2 and bar. When x1 and bar and x2 and bar are both positive, then what we have is theta 1 bigger than this positive number times theta 2, and theta 1 is less than or equal to x2 times theta 2. That's also a positive number. So you can draw these boundary lines for these two inequalities. So this, I'm going to make this blue so that it matches the curve's color. Right, so the boundary line for this inequality is this blue line, and the boundary for this orange inequality is this orange line, right? So the values of theta that satisfy this inequality are to the right of the blue line, and the value of theta that satisfy the orange inequality are to the left of the orange line. Their intersection is this theta n hat set, and that is this cone, right? This small cone. This cone is very close to the vertical line, which is the identified set, but not in the Hausdorff sense, because the Hausdorff distance is also going to measure the points in the identified set to the theta n hat. And that distance in this case can be very large, right? So it can be very large. And that the Hausdorff distance in this case is very large, is infinity if you don't bound theta 1 and theta 2. If you bound it by b, then it's going to be b, right? And that's one case. You can consider all the cases. Why? So this is the case when x1 and bar is positive, x2 and bar is less than 0. Then the boundary line corresponding to the first inequality is this curve, and the boundary line corresponding to the second inequality is this curve. And the first inequality requires the point to be on the right of this blue line, and the second inequality requires the point to be on the left of the orange line. So the intersection is going to be this cone. This cone is also around the identified set, right? But it's not close to the identified set in the Hausdorff sense, because the Hausdorff distance is also going to measure the points here to this estimated cone, right? So, and that can be very big. And you can go through all the cases, and you can see in every case, the estimated set will only get at half of the identified set, right? Not the whole thing. And the Hausdorff distance is always infinity, and it doesn't go to 0 no matter how big n is. So that's what I mean by it's easy to get to part of the identified set, but not the whole thing. So with probability 1, the Hausdorff distance is infinity at any sample size. And bounding the parameter space to some bounded set does not help much, because then you just reduce the Hausdorff distance to b, right, from infinity, and that's still nowhere close to 0. So estimating the identified set is difficult. The literature has made several attempts to establish set consistency. You can only do this by ruling out bad cases like the one that's just discussed. These are some of the papers that make such assumptions that rule out bad cases. But these conditions, if you look at them, they are not intuitive and not easy to verify in practice. And sometimes they are very restrictive as well. So yeah, so my paper is one of them, and I do not claim that is a very easy to justify condition that we make. So as you can see, so the argument set or the sample analog estimator for identified set doesn't work usually. One idea is to, the argument set or the sample analog estimator, we see it is too small, right? If it is too small, can we just expand it in some way so that it's not too small, right? This idea is, adding a tolerance. So adding a tolerance, that's you first construct a criterion function like a GMM criterion function, and you instead of requiring this criterion function to be 0, you allow a positive tolerance to this criterion function. I think this criterion function is not correct. I should say it's the negative part of the first moment function and positive part of the second moment function. So setting the set of values, setting this criterion function to 0 is too small, but we can make that bigger by allowing a tolerance to that. And if the tolerance goes to 0 slowly enough, then the enlarged set with the tolerance can be shown to be consistent in Hausdorff distance. Okay, so theoretically that is a solution. But in practice, as you can see, there is no real guidance for how this epsilon intolerance should be chosen for consistency. And in a problem like this, the tolerance is just going to be make this line a bit bigger, so makes this cone a bit bigger, and the set is very sensitive to the tolerance, right? So it's kind of hard to get a good guidance for choosing the tolerance, and the result is sensitive to the tolerance. So therefore, this is theoretically a solution, but in practice, it's not a great solution. And because of this kind of difficulties in obtaining consistent set estimators, the literature has turned to confidence set instead. And confidence set is better because confidence set is going to give you a tolerance that's dependent on the noise level in a sample. And that is kind of a more disciplined way to come up with set estimator. So typically you cannot show Hausdorff distance for these estimators, but you can show coverage probabilities. So there are two types of confidence set considered in the literature according to the target that they cover. One confidence set is confidence set for the identified set. So that's a confidence set that will cover the whole identified set with a pre-specified probability. And another is a confidence set for the true parameter value, or the confidence set for each value in the identified set. So this confidence set does not aim to cover the whole set, but it covers every point in the identified set with at least this pre-specified probability. And both are reasonable generalizations to the confidence sets in the point identified case. So both are natural generalizations. I mean, conceptually, I don't think one is better than the other, but typically the one that aim at each point in the identified set is narrower and therefore is probably more welcome in practice if you don't want the bounds to be too large, okay? So Let's focus on confidence set for the true parameter values today, because that's the type that received more attention in the literature. Constructing such a confidence set is done by test inversion. I think everybody here knows how to do test inversion, but I would just go over it anyway. So what one do is to construct a test for the null hypothesis that the true value equals a given value, a hypothetical value theta. And the test is going to depend on this hypothetical value, right? So at some hypothetical value, the null hypothesis would be rejected. At some other values, the null hypothesis is not rejected. So you collect the values that are not rejected, and that collection forms this confidence set. If the test you construct for this null hypothesis has uniform size, then the confidence set you construct this way also has uniform coverage probability. So that's constructing confidence sets for via test inversion. So the so testing theta naught equals theta really just amounts to testing whether this inequality and equality constraints hold or not at this theta value, because these inequalities are the only empirical content for true value equals theta, right? So the inference problem for moment inequality model reduces to testing a bunch of equalities and inequalities. And now let's consider an IID sample. There, it could be a time series sample, but it's easier to talk about IID sample. To test this set of inequalities and equality restrictions, we can construct a test statistic and a critical value as we normally do for any testing problem. And the test statistic and the critical value will make use of some of the statistics. One of the statistics is the sample average of the moment function. Well, that is the most efficient estimator for the population mean, because the hypothesis is for the population mean. It's obvious that this sample mean would be useful, right? So we use this sample mean for the moment functions. And we also use the sample variance covariance matrix of the moment function. Okay, we use sigma n to denote the variance covariance matrix, and the little sigma n j to denote the jth element on the main diagonal. So that's the estimated variance for the j's moment function. And some of the test statistics used in the literature are of the following form. So we have this one possible test statistic is the max test statistic. So different test statistics are different ways to put together the information in the sample average and the variance covariance matrix, right? So these are different ways to measure how much the moment equality and inequalities are violated in finite sample or MN bar, right? So the max statistic takes the maximum of the violations to the moment equalities and inequalities, right? So maximum violations. So for the first P moment condition, these are equalities. So as long as this is non-zero, MN bar J is non-zero, we can say that is a violation in finite sample. So you take the absolute value of that violation. And that violation is standardized by the variance, which is always a wise thing to do. And for the next K minus P moment conditions, these are inequalities. So only the negative parts are violations to the moment restrictions, to the hypothesis. So we only measure the negative part. Okay. And and studentize that moment by the standard deviation estimator as well. So the max statistic takes the maximum of all the violations, and the sum statistic basically sums up the violations, right? Square of the violations. And there is a third one, which is good in some sense and bad in some other sense. This one is the quasi-likelihood ratio statistic. It would be the likelihood ratio statistic if M bar is in fact normal. If M bar is normal, then this QLR statistic is the actual likelihood ratio statistic, right? So this quasi-likelihood ratio statistic is also easy to understand. It measures the distance between the sample average and the null space, right? The space of the population mean for the moment function allowed by the null hypothesis. And so it's a distance measure of M bar to the null space. And we use a quadratic form distance with the inverse variance weighting, right? So this statistic is good in the sense that it uses inverse variance weighting, and inverse variance weighting in many other problems is shown to be to yield like powerful tests and efficient estimators. And in this problem, it has not been shown to have those properties, but you would think that using all the information in the variance covariance matrix is a good thing, right? It can lead to more power in some interesting directions, right? So that's the good thing about the QLR. And in fact, in some of the papers in the literature, they found this test does have better power in many cases. But there is also something bad about this statistic, that is, it requires this quadratic minimization. Well, these other two do not have this minimization problem in it. So computationally, this is a bit hard to do. And there is another bad thing about it, that is it uses the whole variance covariance matrix. I just said that it's good to use the whole variance covariance matrix because they provide information about the correlation between the moment conditions, but it's also bad because then it requires more information, requires a good estimator for all the elements in the variance covariance matrix, right? So, but anyway, there are these three different kinds of variance test statistic that the literature has come up with to test the moment inequality and equalities. So yeah, so as I said, it kind of resembled the optimally weighted GMM criterion function for equality models. These three test statistics are all special cases of the general form. The general form takes a function S, apply it on the scaled sample moment and the sample variance covariance matrix. This function S is this for the max, and it's this sum for the sum statistic, and it's this quadratic form for the QLR. So in all cases, they have something in common, that is they are all homogeneous of degree 1 in this case, and degree 2 in this case in M. And what's more important, they are all a monotone in some components of M, not all. They are all monotone in the last K minus P components of M, right? Because here it's measuring the negative part. Therefore, when M is bigger, the negative part is smaller. So it's decreasing in the K minus P, in the last K minus P elements of M. And the same thing with the sum, same thing with the QLR. And this monotonicity will be important for coming up with critical values. Yeah, so as I said, common property, they're all decreasing in the p+1 to the kth argument. Okay, and they're all continuous and they're all scale invariant. We want to construct an appropriate critical value. So we want to study the limiting distribution of the test statistic for under the null, that is for theta in the identified set. So for any given point theta in the identified set, this is the test statistic, right? So that's the test statistic that we wrote down. Is the S function applied on the scaled sample moments and the sample variance covariance matrix. What we are going to do is to add and subtract the population expectation of the moment function to this first argument. When we do that, we create this new n theta term, which is root n m bar minus em w theta. But then we also have this root n population mean left here. This new n part is clearly something that we can use Gaussian approximation for, right? By central limit theorem, under fairly general conditions, this is asymptotically normal with variance 0 and variance with mean 0 and variance covariance matrix given by the variance of the moment function mw theta. So that part is easily approximated by Gaussian or by bootstrap, because this is also a form that you can use bootstrap to approximate. And sigma n hat, that also has a non-degenerate limit, has a non-random limit. That part is also easy to deal with. It's non-random in the limit. And this part is random, but you can approximate it by Gaussian. But this red part is kind of troublesome because that is an unknown deterministic quantity, right? We do not know this. If we knew this population expectation, we wouldn't be testing the moment inequalities, right? So we do not know this, and that is square root n times the population mean. It also cannot be consistently estimated because of the square root n scale, right? This is the population mean. You can estimate the population mean in regular cases. You can estimate this at most root n consistently. So root n times this cannot be estimated consistently. So this part is unknown and cannot be consistently estimated. So the null distribution of T and theta cannot be approximately, cannot be feasibly approximated, right? Because there is a term that cannot be consistently estimated. However, the null distribution of T and theta can be bounded. How do we bound it? We can recall that S has a monotonicity property. S is monotonically decreasing in the last k minus p elements. Okay, so we know for the first p element, this is known because these are equality constraints which set em w theta to 0. So the first p element of this part are actually known. So, but the next k minus p elements are not known. They are only known to be non-negative. Well, they are known to be non-negative. If they are say positive, strictly positive, then we say the moment inequality J is a slack moment inequality. If EMJW theta equals 0, we say that the moment inequality is binding, not slack. And root n times EM is also called the slackness parameter. And that slackness parameter cannot be estimated consistently, but it can be bounded. And there are 5 different critical values that we will talk about that will use this monotonicity of S and bounds for the slackness parameter to come up with critical values. So I'll talk about 5 different critical values. The first critical value that the literature came up with is the plug-in asymptotic critical value. This plug-in asymptotic critical value is in some sense a least favorable critical value. It replaces the unknown value of the slackness parameter by 0, right? We know under the null hypothesis, these unknown parameters are non-negative. If we replace it by 0, we reduce the value of the first argument of the function S, right? If we replace it by 0, then we reduce the value of the first argument. Then due to the monotone decreasing property of the S function, you increase the whole function S, right? So by plugging in 0, you obtain an upper bound. You obtain an upper bound for the null distribution of the test statistic, right? Or for the asymptotic approximation of the null distribution of the test statistic, right? So replacing it by 0, you obtain an upper bound. And once you replace it by 0, there is nothing that cannot be estimated consistently in this S function. So you can simulate the normal random vector, you can estimate the sigma hat matrix, and then you can compute a simulated quantile and use that as the critical value. Okay? And that is the plug-in asymptotics critical value. That critical value, because we made the distribution bigger before we come up with this critical value is big enough. It's not too small. So it does have asymptotic size control. So it controls the size of the test. And so that's the first critical value that we use. And this critical value, it's shown to have asymptotic size control. And I also want to stress that it has uniform asymptotic size control. And I want to sidetrack a little bit from talking about critical values to talk about uniform asymptotic size control a little bit, because that's something that you hear a lot in this literature. So what does uniform asymptotic size control mean? To see what it means, let's make it explicit that the distribution of the data is P. So P is the true data distribution or true data generating process, and make that P explicit in the expectation as well. So E sub P is expectation under this distribution. And also the ID set, clearly it also depends on P because it depends on the EP, right? Identified set also depends on P. So a critical value that achieves asymptotic uniform size control if the limit of the inf of the coverage probability, I'm sorry, this is a test, not the confidence set, right? So this is about the test. So the test with the critical value Cn achieves asymptotic uniform control if the limit of, then I think this should be, sorry about that. So this if should be sum, should be sup. So we measure the maximum rejection probability for every point. Maximization is taken over every point in the identified set and also taken over all possible data generating process satisfying model assumptions. And this supremum of rejection probability is by definition, I didn't write that, by definition, the size of the test. Of the test that reject the null if Tn is bigger than the critical value. So the supremum is the size, because size is defined to be the worst rejection rate under the null hypothesis. And the uniform size control simply requires the limit of the size is bounded by alpha. And the limit is taken before, after you take the supremum. So these are all supremum. And when this requirement holds, we say that the test has uniform size control, uniform asymptotic size control. That is contrast to the pointwise asymptotic size control. Pointwise size asymptotic size control simply requires that the limit of the rejection probability is less than or equal to alpha at fixed true data generating process and fixed value in the identified set. So as you can see, the uniform size control is a stronger requirement than the pointwise size control. And what's the consequence when pointwise asymptotic size control holds, but the uniform asymptotic size control does not hold? What if you only have this, but not that? Then that means limit of this sup is not less than or equal to alpha. And mathematically, that's equivalent to saying there is a positive number C for any sample size n, no matter how large. There exists a P and a theta such that the probability of rejection is bigger than alpha plus C. So if you have pointwise asymptotic size control, but fail the uniform asymptotic size control, then at any sample size, you can find the case that's consistent with your model assumptions, where the test reject the null with probability strictly bigger than alpha. And that is kind of a size distortion for the test. Just to show you an example where that could happen, consider this stylist example where you are considering a lower bound and an upper bound for a parameter theta. And the lower and upper bound variable YL and YU follow this distribution P, and we have an IID sample from P. Now, suppose you consider this set of DGPs consistent with your assumptions. This set of the DGP allows the identified set or identified interval for theta. So that is the length of the identified interval for theta. It requires the length of the interval to be strictly positive. And then it also imposes some moment conditions. And let's say for simplicity, we assume the bounding variables have variance 1. They don't have to, but when they have variance 1, I don't have to worry about studentization. Then the following confidence interval will satisfy pointwise asymptotic size control. You can add a one-sided normal critical value divided by root n to the estimator for the upper bound variable, a sample mean of the upper bound variable, and subtract the same thing from the sample mean of the lower bound variable. Then this confidence interval has point-wise size control. So that means probability that, say, for example, EYL, which is the lower bound of the identified set, belongs to this interval we can show that is going to alpha, right? So because that is because probability of that value is in that interval, is in this interval, is equivalent to YL bar minus EYL is greater than Z alpha over root n, as well as YU bar minus EYL is greater than Z alpha over root n. Right, so that probability, this is, let's see, we assume that variance is 1, so this is root n times this. So if I move the root n over there, so I move the root n to the other side, and that's going to be asymptotically normal with mean 0 and variance 1. But this part is root n YU minus EYU plus EYU minus EYL, which is the length of the interval. Times the root n. Length of the interval is positive for every given p. So root n times that positive number is going to infinity. And this goes to normal 0, 1. So therefore, that probability goes to probability of normal 0, 1 bigger than Z alpha, and that is alpha. And you can find that this interval covers not only the lower bound of the identified set with probability alpha, but also the upper bound with probability with asymptotic probability alpha. So this interval does have the correct coverage probability point-wise. So correct asymptotic coverage probability point-wise, but it does not have very good finite sample coverage probability. So in finite sample, you can find that, now additionally, suppose that YL is normal 0, 1, and YU is YL plus delta. Delta is the length of the interval. Then in finite sample, you can find the coverage probability of the interval is actually psi of Z alpha minus psi of minus alpha, Z alpha minus root n delta. So that is, this part is y minus alpha. Well, this part is positive. Depending on what delta is, it could be a bigger positive number. Therefore, this difference is clearly less than 1 minus alpha, right? So in finite sample, this could be very different from 1 minus alpha, depending on what delta value is, right? So even though there is point-wise asymptotic correct coverage in finite sample, the coverage can be pretty bad. Okay. So this example is from Inference and Mansky, and that is the motivation for focusing on uniform asymptotic size control. If you ensure uniform asymptotic size control, you will not have this finite sample size distortion problem. It's in fact not very hard to achieve uniform asymptotic size control in moment inequality models. Like for the stylist example, uniform asymptotic size control can be achieved by replacing the one-sided critical value by the two-sided critical value. Then this has uniform asymptotic size control. And that is equivalent to the max PA confidence set. So the confidence set based on the max test statistic and the plug-in asymptotic critical value reduces to this. And so that is one critical value that has uniform asymptotic size control. We have 4 more critical values that also achieve uniform asymptotic size control, but they are smaller than the PA. So potentially they lead more powerful test and narrower confidence set. So one such procedure is subsampling. Recall that the test statistic we construct is of this form. We can construct a subsampling critical value by following these steps. So subsampling, we all know how to do it. We simply draw a subsample of size Bn. Bn is a smaller order than n. And then you calculate the subsample analog of the test statistic. Right? So basically you calculate the same statistic and plug in the S function, but using the subsample. You repeat the subsample calculation like capital B times for capital B subsamples. You take the 1 minus alpha quantile of the B values. That will be the subsample critical value. Okay, so that's the generic subsample critical value. And the subsample critical value is valid asymptotically and uniformly asymptotically in this context, because when you expand the subsample statistic, you find a similar structure as the expansion for the full sample statistic. So you're gonna get a asymptotically Gaussian term plus a slackness parameter. The asymptotically Gaussian term is asymptotically the same as nu n theta. It might be more variable than nu n theta, but asymptotically they have the same distribution. Okay. So that part approximate nu n theta quite well in large samples. And this sigma n hat part is also a consistent estimator for the variance covariance matrix. And this term is not the same as root n as the slackness parameter, root n times EMW theta. It's not the same, but it's in the right direction. It is less than or equal to root n EMW theta, simply because root Bn is smaller than root n, right? So therefore, this statistic stochastically dominate the version with root n instead of root Bn, right? So the subsample statistic has a distribution that asymptotically dominate the null distribution of the test statistic. And because of this, the subsample provides an upper bound for the null distribution. Because of this, it achieves uniform asymptotic size control as well. And the third critical value is the generalized moment selection critical value. So instead of replacing this slackness parameter by 0, as the plugin asymptotics does, we try to kind of get a conservative estimator for what this is, right? We cannot get a consistent estimator for this because of the root n, but we can kind of get a conservative estimator for this. So if w theta is positive, then root n times this will be big for n big, right? Then if we can know that based on the information provided by the sample mean, then we can set the slackness parameter to infinity, to positive infinity. Or in other words, when you set this to infinity, that moment condition will not appear in the test statistic or in the critical value calculation. So it's just by doing that, you get rid of the very slack inequalities. But you don't want to do this too aggressively. You only want to do this when you are sure that root n times EMJ is infinity, right? So what the GMS critical value is doing is to replace the slackness parameter, the J slackness parameter by 0. If when you do, if this standardized version of root n m and bar is not very big comparing with a threshold kappa n. So that's when we are not sure, we cannot determine that the moment is slack. But if this statistic is bigger than the threshold, then we are sure with probability approaching 1 that the moment is slack. In that case, we can set the moment selection function to infinity. That's, we replace that corresponding element of the slackness parameter by infinity. And that threshold needs to diverge to infinity in order for this to be not too aggressive, okay? So the generalized moment selection critical value is the same as the plugin asymptotics. You use the normal random vector to approximate the nu n, and you use the GMS function, generalized moment selection function, to replace the slackness parameter. And you simulate a quantile from this distribution, and that quantile will be the critical value. This critical value also achieves uniform asymptotic size control because it only takes a moment as slack when we are sure that root n times EM goes to infinity. So EMJ, because we look at each moment separately, right? And we only take a moment as slack when this goes to infinity, in which case we should be taking that moment as slack because it is slack, right? So we're not making mistake by discarding the moment inequalities that are not very slack, okay? So that is the reason that it also achieves uniform asymptotic size control. So that's the third critical value, but you may have noticed that there is a threshold parameter kappa n that's an input into the GMS function. And that is a tuning parameter. That is required to diverge to infinity, but slowly. That tuning parameter is user chosen, and it could affect the size and the power of the test. So that is And there isn't a simple guidance for how kappa n should be chosen, other than it should diverge slowly with n. So there are different ideas for how to deal with the tuning parameter. One idea is proposed by Anderson-Barwick. Anderson-Barwick basically considers a fixed k asymptotics. It's like the fixed bandwidth asymptotics in non-parametrics, fixed kappa asymptotics. So they consider the asymptotic size of the test when you fix kappa instead of letting it be a diverging sequence. When you fix kappa instead of letting it diverge, the asymptotic size of the test is not controlled at alpha. So with that fixed kappa, you have to couple it with a size correction. Okay. And you need to calculate the asymptotic size at that fixed kappa and do a size correction. That correction will be a constant added to the critical value, okay? Because the critical value now is not correct. It's doing generalized moment selection too aggressively. So we need to do a size correction. And then still, how do you choose the fixed value of kappa? They propose to choose the fixed critical value kappa, fixed tuning parameter, fixed threshold kappa, by maximizing a weighted average local power. This whole enterprise is computationally very intensive, because in order to come up with the size correction constant, you need to have a good idea of what the asymptotic size is for each given kappa. And what is asymptotic size? Or what is the size of the test? That is the maximum rejection probability over all the values of theta in the parameter space, right? Sorry, in the identified set, I'm sorry, in the identified set. So calculating or simulating this asymptotic size is difficult because you have to consider many points in the identified set. So just calculating or approximating or simulating the asymptotic size is computationally intensive, but that is needed to come up with the size correction. But you add on top of that a maximization of weighted average power to choose kappa. So that makes it just even more computationally intensive. So the whole enterprise is very computationally intensive, both because you have to calculate the asymptotic size and because you have to maximize a weighted average local power. But fortunately, you don't have to do this whole thing for k less than or equal to 10. That is when you have at most 10 inequalities that you're testing. If your problem fortunately has fewer than 10 inequalities, then you don't have to do the calculation for optimal kappa and the size correction yourself. Anderson-Barwick has a table for those values you can just take and use. But in other cases, you have to do the calculation, and that's hard to do. So that's one way to deal with the tuning parameter in generalized moment selection. Another way to deal with the tuning parameter is actually not using the GMS procedure. Instead of using the GMS procedure to approximate the slackness, Romano, Shaikh, and Wolf realizes that root n times the population mean is just a known scaling of the population mean. we have many good inference procedures for population mean parameters. We can construct confidence sets, joint confidence set for the population mean parameter, right? So that's a classical problem that we all know how to solve. We construct a joint confidence set for the population mean parameter, multiply that by square root n, that's going to be a confidence set for the root n times the population mean. Once you have a valid confidence set for the population mean parameter, you can simply take the least favorable value from this confidence set, right? So you take a least favorable value for this from this confidence set and replace the slackness parameter by that least favorable value. The least favorable value is the one that results in the highest critical value statistic value. The least favorable value is the one that results in the highest S function value, right? When you replace root n em by that value, okay? And if the confidence set is a rectangular region, which is not hard to guarantee, then by the monotonicity of the S function, we know the lower left vertex is the least favorable value. In much the same way as using 0 to replace the slackness parameter, we can just use the lower left vertex of that confidence set to replace the slackness parameter. And then we are going to have a confidence set. All right, so this is too much math. So basically, Romano, Shaikh, and Wolf considers a confidence set for root n mu that is of this form. And that is a rectangular set. And we can use the lower left corner of that rectangular confidence set to come up with, to replace, right? So that's the value that you use to replace root n em. And therefore, this is the rectangular region with a lower, okay. Don't remember what I wrote here, but the idea is to come up with the lower rectangular, lower left corner of this confidence region. I'm sorry, so no, this is the lower rectangular region. So I'm sorry, this is wrong. This is the lower left corner of the confidence region for root n mu, and we use that as in place of the generalized moment selection function and put that into the S function. And that is the statistic that we simulate the critical value from. But notice that the critical value is the 1 minus alpha plus beta quantile instead of 1 minus alpha quantile because we have to take into account the noise in constructing the confidence set for root n mu, right? And this beta is kind of a Bonferroni correction for possible non-coverage in the first step. So comparing with the original GMS, there is no longer a tuning parameter for the threshold, but there is a tuning parameter for the Bonferroni, for the confidence level of the first step confidence set for root n mu. But this beta is kind of a better tuning parameter because it doesn't affect the size of the test. It only affects the power. This is not like the kappa n, which affects both the size and the power. So just to sum it up, there are these 5 critical values. Plugging asymptotics is least favorable, has no tuning parameter, but the power is low. Also, computationally is okay. It uses a simulated critical value. It depends a lot on which test statistic you use. Subsampling has a tuning parameter that's the subsample size. Computationally is also similar to PA. Power is higher than plugging asymptotics. GMS has a tuning parameter as well. Power is higher than PA. Computationally is okay. It also depends on whether you use the QLR statistic or the other easier statistics. The Andreessen-Barwick refined the GMS with the fixed kappa, size correction, and optimal kappa that maximizes weighted average power. So that has no tuning parameter at all because you choose the tuning parameter kappa optimally using their procedure. The power is higher, but the computation can be very difficult when you have more than 10 inequalities that you're testing. The Romano-Shaiken-Wolf two-step method has a tuning parameter beta, has kind of a higher power. Computationally is a little bit higher than the first three, but it's not by too much. So these are the 5 critical values that one can use. So far, we have only discussed the test to be inverted, not the confidence set. But the confidence set, remember, it is all the parameter values such that test statistic is not bigger than the critical value. So computing the test once, that is computing the test statistic and the critical value once, is fairly easy for all 5 critical values and all the test statistics, except for refined GMS with more than 10 inequalities. However, remember, doing the test once is not the goal. The goal is to figure out what the set is. To figure out what the set is, you need to test many values of theta. You need to compute the t and the critical value for many different values of theta. And when theta is high dimensional, or not even very high, like 5 or 10 dimensional, this set is a 5 or 10 dimensional set. So what you are really trying to do is to try to find the boundaries of a 5 or 10 dimensional set defined by these inequalities. And that is a difficult problem computationally. So it is desirable to look for computationally easier tests. And I will talk about this other test that is computationally much easier. And this test use analytical critical value that doesn't require simulation for when you calculate the critical value. All 5 critical values I talked about before require simulated critical values. So, and they're harder than just taking a critical value from an analytical distribution. And this test use analytical critical value and the quasi-likelihood ratio statistic. That's a statistic I introduced before already. And so the statistic is something that other tests also use, but the critical value is different. How do you define the critical value in this case? You take Tn to be the solution to this minimization problem. Tn depends on theta. Tn is the unique solution to this minimization problem. So Tn is in fact the non-restricted estimator of the population mean. So Tn is the non-restricted estimator of the population mean. And we are going to count the number of elements in Tn that are equal to 0. And let Dn be the number of such elements. Then this simple critical value will simply be a chi-square critical value, or the 1 minus alpha quantile of the chi-square distribution, where the degree of freedom is the number of 0 elements in this Tn vector, okay, in this restricted estimator of the population mean. So this test is kind of very easy to compute because it doesn't use simulated critical value. It also doesn't use a tuning parameter. So it doesn't require any optimal choice of the tuning parameter. The test also has uniform asymptotic size control. And it's easy to implement. There is no tuning parameter, and the power is comparable to these more complicated methods. So just comparing CC has no tuning parameter, and the computation is much easier. And there is another easy alternative, computationally easy alternative, that's in Andrews, Rath, and Pecos, also a working paper. This other test also, one version of it, it doesn't use a simulated critical value. It uses the max statistic, max of the violation of each of the sample moments. Okay. They also use a conditional critical value. They observe that conditional on J hat equals a given value J. So J hat is the one that achieves this maximum, the identity of the maximum moment. Conditional on the identity of the maximum of the moment, as well as the value of the second largest. Okay. The maximum is a truncated normal or asymptotically truncated normal with an unknown non-positive mean, unit variance, and known lower truncation. So the truncation point is known, but the mean is not known. However, this truncated distribution is decreasing in the mean. So if you know that the non-positive mean, the mean is non-positive, and you replace it by 0, so it's non-decreasing, non-decreasing in that mean. So if you replace this non-positive mean by 0, you make the statistic bigger. So if you come up with the critical value, that way, the critical value is not too small, right? So you still come up with an upper bound for the limiting distribution of the test statistic. So then they propose a critical value from the truncated normal with 0 mean, unit variance, and a known lower truncation. This test has exact uniform asymptotic size as well. It's also very easy to implement, but unfortunately, it has some undesirable power property when the largest moment is kind of close to the second largest. It's easy to see why, because the second largest is the truncation point, right? If the truncation point is not really different from your test statistic, then the test is not going to reject, because their critical value would be at least as big as the truncation point, right? Because critical value comes from the truncated distribution. Okay, if the max and the second max are close, then the test is not going to reject. So the rejection region of the test, if you draw it for a 2-vector case, for 2 inequality case, the rejection region is kind of look like this. So that's the 45-degree line. So you reject in this shaded region. So this is the null. And as you can see, these points are very far away from the null on the 45-degree line, but you're not going to be able to reject any point on this line just because the largest and the second largest are the same on this line. Okay. So because of this undesirable property, they also propose a least favorable test that's kind of close to the PA test. It's the same as the PA test. They hybrid the conditional test with the PA test, and that hybrid test seemed to work better. So yeah, so that's everything I want to say about unconditional moment inequalities.
So thanks, Xiaxia. So I think it's pretty late in the US, and thank you very much for giving us stay late in the night to give us these lectures. So I will cut the questions. So in 2 days, on Thursday, we're going to have the remaining 2 lectures. So if anyone have questions, maybe we can move the questions to that day. So let's
Okay.
call it a day. Have a good night, Xiaxia. Thank you.
Thank you.
Yeah.
Yeah.
Bye bye，小霞，辛苦了。Thank you, thank you.
Bye.
Yeah. Have a good night.
Good night.